is not a problem. So the denominator, when age approaches 0, this exists and this exists. Not the denominator is the problem, but this is what we just did a minute ago.
You multiply by the conjugate?
Thank you very much. The square root of x plus the square root of x plus age, the square root of x plus the square root of x plus age. So then limit as age approaches 0. Here's the denominator. Who can give us the numerator? Gia, you want to try it again?
Yeah, sure.
Good.
It'll be x minus h.
First term squared minus the second term squared.
Oh, so it'll be x plus h?
But in parentheses.
In parentheses.
Great job. Thank you. So now, of course, when I distribute here, I have limit as age approaches 0, x minus age. Careful, that's why we need to put in parentheses, because you may forget to distribute to the second term, the negative sign. So age, 1 plus the square root of x, 1 plus the square root of x plus age, the square root of x plus the square root of x plus age. And of course, you're going to say this. I don't like to do this, but I'm going to say this will go away with this. I should write it one more time. I should not be lazy. So now I drop the limit operator. Can anyone give us the answer?
Would it be -1 over 1, or open parenthesis 1 plus square root of x, close parenthesis, open parenthesis 1 plus the rest of the equation? What was that?
No, it has age in it. I'm dropping the limit operator. I can't just copy that again, right?
Oh, you're right.
So then, so this is accounted for.
So it would be 1 plus square root of x squared.
Excellent. This is accounted for.
Square root of x plus square root of x.
Which is an apple plus
X.
an apple. No. An apple plus an apple is
2 square root x.
2 apples. Very good. Great job. Thank you. Okay. Let's move on. What I would like to, we haven't finished, of course, but I'd like to look at some problems from 2.8. So, at the end of 2.8, I did print out some pages that I would like to look at. So if you cannot see this, I will copy the problem. So I would like us to graph an approximate graph of a derivative. I don't know if you can see. It's probably not good enough. So it says match the graph with the graph of its derivative. I'm not going to do that. I just would like to choose a function from a to d, one option, or choose a function here and graph its derivative. Anyone would like to pick, or I will? Okay, I'm going to pick this one, D. So obviously D is a polynomial function. I'm going to enlarge it here on paper. So it's something like this. right exactly right under, extending the vertical, the y-axis, and a horizontal or x-axis. This is our function, and we want to sketch a graph of its derivative. Before I do that, I want to explain one thing, and I'll come back to the graph. So, can I determine the slope of this line? The answer is yes. I can create a right triangle, and if I can estimate the rise and the run, I will say the slope of this for me is, let's say, 1 and 2, roughly. It appears sort of that this is 1 unit and this is 2 units. So then I'll say the slope is 1/2 and positive. Now, does it matter if I use this triangle, or let's say I extend the line and I use this triangle? It's not going to make any difference because they're similar triangles. So if I use this and I say it's 4, then this is double, which is 8. So it doesn't matter. I can even use this triangle. And I'll say this is 0.4 and this is 0.2. And I still get the same slope. So it doesn't matter how small or how big a triangle, because the slope will always be the same. So why I need this concept? By similar triangles, it's going to be the same. Still rise over run. And they will still be proportional, no matter how long the line or how short the line I use to determine the slope of the hypotenuse. It doesn't matter. So how do I, from a graph of a function, how do I sketch the graph of its derivative? So here's how we do it. I'm going to start with the easy points. And I see that at this point, the slope is this. But what is the slope of a horizontal line?
1.
0.
Thank you. So the slope of this line is 0. So obviously, I'm here graphing the slope of that graph at any point. I'm not going to use 1,500 points. I'm going to use few points so I can sketch the graph. It's going to be an approximation, but quite a good approximation. Here's another easy point. And here's another easy point. And of course, I have to follow the x value. And I will identify what happens there. But at this point, I'm going to graph the point corresponding to the derivative. At this point, I'm going to graph the point corresponding to the derivative. So I'm graphing this slope, the tangent, and what is the slope of this line, and what is the slope of that line?
It's going to be 0 and 0.
Very good. So I determined already 3 points for the derivative function. Okay. So now something very important that we need for the next chapter. Can anyone tell us what does the function do between negative infinity and this point? For x between negative infinity and this point, what does the function do?
Changes.
That's awesome, but can you say it again? I didn't hear. I mean, I know you said it. You said something, but I'm not sure.
It increases.
Exactly. So every time a function increases, what will be the slope of the tangent? What kind of slope will it be?
Positive.
Positive.
Exactly. So you can make yourself a note. We're going to discuss this later. So the function is increasing. the first derivative is positive. And we see that. So now you see that it's positive. The first derivative is positive, but let's pick some values. So I'm going to use this point. So I'm going to draw the tangent. I'm going to draw a right triangle. I know it's hard, it's not easy. And I'm going to say this looks like 3 units and this looks like 1 unit. So at this point, which corresponds to this x value here, I found positive 3. 1, 2, 3. So it's this point. For this x value, I found that the slope is 3/1. Roughly, it's an approximation. So then the first derivative, the derivative at this point, this x value, whatever that is 3. Okay, I'm going to choose a different point. I'm going to draw the tangent. And I'm going to say, this is definitely smaller. Here, it's very clear that the slope is much higher than here. Here the slope is smaller, and here the slope is smaller, and here the slope is smaller, and here the slope is still positive, but now it's 0. So at this point, the slope is 2. At this point, it's much higher. So it comes from big positive values, comes down to 3, comes down to 2, comes down to 1, comes down to 0. So here is my graph of the derivative function between -infinity and this value, whatever that is. Okay, at this point, I'm going to say it's -1. At this point, and so on and so forth, till it comes to 0. So the function itself decreases. So when the function decreases, its derivative has to be negative. So till a certain point where the derivative is maximum negative, but then it has to come back to 0. How do I know? Right here. I already have this point established from the beginning. Okay, so now what happens is positive and then negative, right? So it's increasing, so the derivative will be positive till a certain point where it's maximum. Somewhere here will be maximum positive, and it will come down to 0. How do I know? It's because I already have that point established. And from this moment on, the function decreases, so the derivative will be negative. So this is the mechanism. We create an estimate or an approximate graph of the derivative from the function. And we can also reverse the step. We can start with the derivative and determine the function. Any questions here? Anyone?
So you're pretty much graphing the slope, kind of?
That's what the derivative is.
Oh, okay.
That's exactly what the derivative is. That's exactly what the derivative is. It's the slope of the tangent line to the graph up, or the instantaneous rate of change at any point where the function is differentiable. That's exactly what it means. The slope is the instantaneous rate of change. And that's exactly what we did. That's what the function represents. Any questions on this? Any questions? Anyone? Okay. Enough of graphing. It takes a long time to explain step by step, but it's very important. Okay, So I would like to look at, and now we have this in the book. So let me share my screen. Oh, there is a chat. Is that for me? Yes. You are excused for bathroom, of course. Okay, so I'm sharing the, I'm sharing, where are you guys? I lost you. I can't find you. Okay, here you are. Okay, I'm sharing my screen. And where is my... Here it is. Here's my book. Okay. I like to look at a problem like this. Anyone would like to pick? So the question is asking, state with reasons the numbers at which f is not differentiable. So let's look at 42. Okay. So can anyone tell us where is this function not differentiable?
-1 and 2.
-1 and 2. Why is it non-differentiable at -1?
Because it's a jump.
Because the function is not continuous. Okay, the function has to be continuous for it to be differentiable at a point. If the function is not continuous, it cannot be differentiable. Good. Why is that differentiable at 2?
Because it's not like a tangent line or something.
It's called
The cusp.
cusp. Very good. Has a vertical tangent. It's a cusp. Perfect. Okay. Moving on. Okay, so I think we should go back now to 2.7 because I have a few things to say about 2.7. Okay, so that was 2.8, which talked about the derivative function. So now we do have in 2.7 two things to talk about. There are two definitions for f prime of a. Can anyone tell us what do you think? Anyone? Any volunteer? What do you think f prime of a is? We talked about f prime of x so far. What will f prime of a represent? What do you think? Anyone? Even if you don't know anything about calculus, we should be able to say what f prime of a represents versus f prime of x. What's the difference?
The derivative of f of a.
Yeah, so what is the difference between these two?
That would be the instantaneous moment of A.
So this is the function value at a. This is the value of f prime of x at x equals a. So this is a specific value of the function, right? This is the function in general. This is the value of this function when x equals a. Okay, there we have two definitions for this. Why two definitions, and which one do I use when? Well, I have to say that for certain functions, one definition is easier than the other. But I cannot give a general recipe. So f prime of a can be limit sh approaches 0 from f of a plus h minus f of a divided by h. This is identical. I just replaced a by x by a. It's the same thing with this one. So I replaced x by a. I have a plus h, a, and everything else is the same. So there is no big deal here. And there is a second definition, which is the limit as x approaches a from f of x minus f of a divided by x minus a. Same thing. Sometimes this one is easier for certain functions to work with and determine f prime of a. Now, do you really have to use one or the other? If the problem is asking you to, yes. But if the problem is not asking you to use f prime of a, one of the two definitions, then you can use f prime of x, and then at the very end, replace x by a. That's fine. But I would like to practice maybe not this one, but this one for any function you would like to pick. So pick a function so that we can determine f prime of a using this definition. Any function? Can anyone give us a quadratic function? Anyone? A quadratic function, anyone?